Let's take a look at half-lives. If you talked about nuclear chemistry in your first year class, then you'll know what half-lives are. If you've talked about them in a previous science class, you'll know what they are. Definition of half-life. It's the amount of time needed for 1/2 of the reactant to be used up. If I start with first order reactions, when the time I'm interested in equals the half-life time, so when T equals T1/2, my concentration of reactant is equal to half of my initial concentration, and that's simply what that equation says. So if I take a look at this natural log equation, where I have natural log of the initial concentration over my concentration at time t equaling kT, when I'm at the half-life, then I can substitute 2A in for the concentration of my substance initially, or the initial concentration. And what I get then is the natural log of 2 equals K times my T1/2. I can rewrite that. If I know K, then I can find the half-life time for my reaction. If I look at the graph, if I start with an initial concentration of 0.1, half of that's going to be a concentration of 0.05 molar. It takes this much time, 100 seconds, to get there. So T1/2 in this case is 100 seconds. To go from 0.5 to 0.05 to 0.025, that's to here. That's another 100 seconds. If I'm going to go to 0.0125, that's half of my previous concentration. That's to here. That's another half-life. So I have gone through 1, 2, 3 half-lives, and I am down to 1/8 of my original starting amount. So the equation in brackets in the red box is probably another one to know. Again, these equations, unfortunately, the integrated rate law equations, the rate equations, the rate laws, the half-life equations are not on your green sheets. So you're going to have to figure out a way to remember those. So for first order, that's what we're looking at. And generally, when we're talking about nuclear chemistry, we're focusing on first order reactions. Second order reactions, a little bit different equation. Again, we take our integrated rate law, which is 1 over the initial concentration equals kT. So if I do the same kind of manipulation, what I'll get for this half-life equation is T1/2 equals K times the initial concentration. So in this case, again, it's based on K, but it's also based on the initial concentration. So first order half-life equation, second order half-life equation are not the same. They are two different things. Finally, let's look at zero order rate laws. We've looked at first order, second order rate laws. Zero order rate laws are really easy. Again, we have the rate expression, the rate equation, and then the rate law. Rate law is really easy. It's just the rate constant. What happens here is the concentration has absolutely no effect on the rate law. If we integrate that, we get an integrated rate law where we have concentration equals negative rate constant times time plus the initial concentration. So there's our straight line equation. If we graph a zero order reaction, our straight line will be concentration versus time. If we want to look at the half-life equation for a zero order reaction, then the time for one half-life is going to be the initial concentration divided by 2 times the rate constant. So that's first order, second order, and zero order rate laws. We're not going to go above second order in this class. It's about as complicated as we're going to get. So we'll take a look at these, we'll take a look at half-life reactions, and we'll do some practice with all of these types of rate equations.